Hi, I'm really pleased to have you here for the Citrus Research Exchange. My name is Camille Crittenden. I'm Deputy Director of Citrus in the Bonato Institute. We have the Research Exchange here every Wednesday at noon, as you probably know, and all of the lectures for the spring are now online. If you would like to go take a look and register for the ones that you haven't registered for yet, there's also a list and a flyer on the table in the back if you want to take a look at that. If you register in time, you get lunch, as many of you already know, and everything that, all the packaging today is compostable, so be sure to stick it in the green bins when you're done. I also want to welcome our web viewers. All of the Research Exchange talks are webcast live, especially to our other Citrus campuses at UC Davis, Merced, and Santa Cruz, but everywhere where there's internet connection as well. They're also archived on our YouTube channel. So if there are other Citrus Research Exchange talks that you want to check out, take a look there, and then this one will also be archived there as well if you want to refer other folks to it. We're really delighted to welcome Greg Dimos here to talk with us today. Greg is a senior researcher at Baidu's Silicon Valley AI Lab. Previously, he was on the research team at NVIDIA. He holds a PhD from Georgia Tech, the Georgia Institute of Technology, where he contributed to the development of the GPU Ocelot Dynamic Compiler, which targeted CPUs and GPUs from the same program representation. His PhD thesis pioneered execution models for heterogeneous processors. So we're really excited with all the burgeoning interest in AI to have Greg here and talk with us about his work at Baidu. Please help me in welcoming him.
Thank you all for coming. You know, these days I have this somewhat of a strange experience, actually, of having a background in computer systems and computer architecture, but working on AI applications at Baidu. So I'm going to try and share a little bit of perspective that isn't entirely focused on artificial intelligence, but kind of spans the entire spectrum of artificial intelligence applications through multiple levels of the hardware and software stack, how they all come together to influence these applications. I thought a good theme for this talk would be this idea that we're at this very interesting point in history with artificial intelligence. I remember when I was a student, we'd always think of these applications as being extremely difficult, as being, you know, of course highly valuable, but just very difficult to make progress on. That didn't stop people from trying, and there was a lot of very good progress that was made, but it was really hard won. And so I kind of think of this as a wall. There's this barrier that's preventing us from making progress here. So the interesting thing about deep learning, really, and its impact on artificial intelligence is that the implication is that this wall really isn't there, that there's some way of getting around it. And making very rapid progress on these applications in a way that wasn't possible in the past. So this talk is going to maybe shed a little bit of light on that. What are the issues? What was different between work in artificial intelligence before deep learning and now after deep learning? And what are the clear opportunities to make very rapid progress going forward? Kind of looking across the entire software stack, from applications to system software to hardware. So let's start with basically what are we talking about when I'm talking about AI applications. It's a very high-level generic term. I want to make it a little bit more specific. I'm really talking about problems that I can fit into this kind of framework, where there's a clear numerically defined input, there's a clear numerically defined output. As an example, maybe I'm doing image recognition, the inputs are pixels, the output is a class of an object. There's some function that I would call my model that's performing this mapping from the input into output. And I'm training this system in order to accomplish an objective. I have a very clearly defined, mathematically defined objective function, which grades how well the system is doing. And then I'm using an optimization algorithm in conjunction with the rest of the system to find good parameters of this function or of this model, try and fit the data set that I actually have. So there are many applications that are hard to put into this framework. If you, like, very importantly, If you don't have clearly defined inputs and outputs, it's hard to get into this framework. If you don't have a clearly defined objective function, you can't write down a mathematical equation that defines, the difference between what the model is doing and what you'd like it to do. It's very hard to apply these applications or these kinds of methods to your application. But even with these limitations, this is a very powerful framework. So the thought is, as I was mentioning before, it's been historically very difficult to make progress on these applications, even the ones that can fit into a framework like this. But we're starting to see some cracks in the wall. We're starting to see basically some way forward in spite of this historical large barrier that we've seen. So why is that? Let's go through the basic building blocks that we need, like the assumptions that we need in order to get this kind of framework to work. So as a prerequisite, we have to assume the existence of some function that does this mapping. If you're doing speech recognition, you might assume the existence of a function that maps from audio impulses into text. We can assert that that function does exist because we see people do it. There is some way of actually accomplishing that task. We can look at other examples like image recognition. Maybe there's another function over pixels that will map those pixels into a class, like maybe a mug or a car or a plane, something like that. This is saying nothing about the complexity of these functions. Of course, for very hard applications, these will be very complicated functions. They might involve time series, they might involve loops, they might involve recursive subroutines. They might involve external memories. They might be very complicated. But we can see examples of systems of people, basically, who are able to perform these tasks successfully, so we can assert that there are functions that do perform this mapping. So that's a prerequisite. We've had some kinds of results that the models that we're able to build are able to approximate these functions. If we imagine that there's a true function that maps space of all pixels into the space of all images of one class, like let's say all possible images of a cat, for example. We assume that that function exists. The second component is we need to be able to actually model it. We need to be able to learn that function. So we have a number of methods that we can use. I'm going to focus on deep neural networks in this talk, but there are many other methods that you can use for doing this. We have this very powerful result for deep neural networks, the universal approximation theorem, that there exists some combination of parameters, number of layers, sizes of layers, choice of nonlinear activation functions in neural networks, such that for a large enough neural network, enough layers, large enough layers, we should be able to approximate any function, even if it's highly nonlinear, even if it's very complicated. So we should be able to model these functions with deep neural networks. And this is the problem. This is the problem that we've always run into. It's possible that you could set the parameters of a neural network in a way that it does model one of these very complex functions. It doesn't say anything about how big that neural network has to be. And most importantly, it doesn't say anything about how difficult it is to find those parameters. We have another result, which is that these problems, if you set them up as continuous optimization problems, they should have an exponential number of local minimum. And it's exponential in the number of model parameters. So if you have a model with 1 million or 1 billion parameters, we have a constant to a factor of 1 billion local minima that you might encounter when trying to find a good fit of one of these models to your problem. And so the thought is that these problems are just intractable, and that you really shouldn't be able to train these networks in a reasonable amount of time for especially very deep networks. And the really big surprise is that even very simple methods can find very good solutions. So the simplest methods that we have, just simple stochastic gradient descent, maybe the simplest possible optimization algorithm that you could think of applying to this problem, is very successful in practice. And this is really surprising. So if you look at this, the result that we've seen is that many applications that were not using these methods previously started using these methods and have, are able to achieve state-of-the-art performance or exceed the previous state-of-the-art. I have a question.
Yes, how does stochastic gradient descent differ from ordinary gradient descent?
Okay, so the question is, how does stochastic gradient descent differ from ordinary gradient descent? Stochastic gradient descent randomly samples a subset of the training set, and then you take you use that sample to compute a estimate of the gradient rather than the true gradient, and then you take a step with that estimate. I'll mention a little bit more details about the optimization algorithm and how it works in just a few slides. Okay. So this is the really surprising result, that this actually ends up working very effectively for many applications. Why is that? We'd like to have some theory that justifies why this is actually happening. The truth is that we don't know at this point. There have been a number of theories that have been proposed for doing this. They're too detailed to go into in a talk at this level. If you're interested, let's see. If you're interested, please catch me afterwards. I can point you at some references for this. But basically, the high-level answer is we don't know. Even all of the theories that have been proposed make assumptions that are too weak to apply to general, very deep neural networks. So I think of this as a clear learning opportunity. We don't know why. We have empirical evidence that what we believe to be true is actually not true. We have an opportunity to learn something. But very importantly, now we have a way forward for many applications. So this graph here tries to put together a very simple flowchart that you can go through if you have a real application and you'd like to make progress on it, and you're not getting the level of performance that you want. You can usually use deep learning to make progress on it. So the idea is, first you need to start with, are humans able to do this? Or is some system able to do this? Can you get an estimate of what the error rate is? For example, it might be difficult to identify a class of various objects, but it's probably easier than predicting the stock market. If you can't find a single person to do this effectively, you're probably not going to be able to find one of these algorithms to do it either. So assuming that you start with that, you go through this process of training your model, training your neural network, looking at your training set error. If it's low enough, then you're good. If it's not low enough, you have a very clear path forward. Previously, you didn't have a path forward here. You could just increase the size of your model, increase the capacity of your model, add more layers, add bigger layers, possibly change the architecture of your model. Once you get your training set low enough, or training error low enough, you can move on to a held out development error set. This is like another word for this is a validation error. If you get to the point where you're also getting good performance here, you can continue to make progress. But if not, you have another clear direction here. You just need more data. So the idea is that as you make your sample of the relationship that you're trying to model larger, then you get a more accurate estimate of this true function. And so you have a path forward in both of these cases, where previously you didn't really have a path forward in the case where the model would not really be able to fit the data. You had to perhaps propose a new algorithm or go and engineer features and feed them into your algorithm. So now there's a clear path forward in all of these cases. The 2 points that should stand out here is that if we keep increasing the model size and we keep increasing the data set size, we're going to eventually run into a computational limit. We're going to eventually run into a problem that's too big for a very large computer to solve. So I'll touch on that in the later slides. Okay. So this is just another graph that tries to capture this effect. And this is one of the biggest trends that we see in deep learning. That previously, if you're in a situation where you increase your data set size, you'd like to get more accuracy on a problem, you could increase it up to a point. But beyond that point, the model would kind of saturate and you wouldn't get any additional performance. And with deep learning, the idea is that you can have a progressively larger and larger model. And as long as you're able to have a computer big enough to train it, you're able to get better and better performance. So this is the number one trend that we see for deep learning. Models keep getting bigger, data sets keep getting bigger. So there's one more trend this enables, really richer outputs. As we start making significant progress on easier problems, we move on to harder problems. And we've gotten really far, actually, for many of these difficult problems. We've moved from few class, like this is an example for image recognition. This applies to many other types of data as well. But using this example, if we start out with a problem that might have previously been difficult, maybe having a few classes, maybe 10 or 2 classes, we're trying to identify, is this a cat or is this a dog? That was previously difficult. That's become very easily solved. We've moved on to large numbers of classes, very specific classes like the specific breed of animal, or very specialized objects like a hand loom. And these dictionaries that have multiple classes will extend into the range of maybe 50,000, 100,000 classes. And models can be built that are very accurate at distinguishing out of those large number of possibilities. And we were actually even seeing progress beyond that, where you can move not just from a fixed number of classes, even if that set is very large, you can move to a sequence of classes. So you can just start outputting English text, as an example, from raw pixels. So if you think about this, we're really just increasing the output size, increasing the set of possible things that we can produce with the model. We're going from a small number of finite classes to all possible English sentences. Both of those are finite sets. English sentences are an enormously large set. Okay. Oh yeah, and I wanted to mention, feel free to ask questions throughout the talk. No need to hold them to the end. Okay. So this is a really bold claim that we're able to make, that this effect actually exists, and especially without having a lot of theory, right? Like without having any theoretical result that justifies why we should be getting these results. So why should we believe this? I personally was very skeptical of these methods. I actually joined this field as a way of learning more and convincing myself whether this was actually real or not. The conclusion that I've come to is that it actually is real. So we can look at the examples. We don't have theory, we can look at empirical evidence. So one high-profile example you've probably heard of is the ImageNet benchmark. This is a large multi-class image classification benchmark. On the right, we're showing examples of some of the classes. And after the introduction of deep learning, or the popularity of deep learning around 2011, you can just see the error rates drop very significantly. Just very rapid progress being made, and achieving around the human level error rate for this particular benchmark. So we also see these methods being applied to diverse applications. One test is, can we make progress in a single domain? Another test is, can we apply the same methods to other domains? So this is another very significant result by DeepMind, or Google's DeepMind group, that basically trained a convolutional neural network to play Go, combination with other algorithms, but a very large component of it was the deep neural network, was able to beat one of the best human players. And this is a very significant result. The previous systems before this AlphaGo system, they were miles behind. They couldn't come close to the best human players. And this was a very rapid progress where we went from not being able to compete with amateurs to be able to beat the best human in the world, or one of the best human players in the world. So some work that we've done at Baidu also, we've looked at image recognition, kind of these large combinatorial optimization problems like Go. We're looking here at another application, speech recognition. So this is an application where basically we're able to take just a deep neural network, put the input is a recording, an audio recording, we call it an utterance. We pass it through a deep neural network. This uses a recurrent neural network, and we predict characters at the output. And so we use this to do speech recognition. So we're able to take exactly the same network and train it on an English data set, and then train it on a Mandarin data set, and achieve state-of-the-art performance in both cases with exactly the same algorithm. The only thing that you change is the data and the character set, and otherwise the algorithm is exactly the same. Internally at Baidu, just as an anecdote, we had a production team, maybe 100 people working on a handcrafted speech recognition engine for Mandarin. This was able to very quickly, within something like a 6-month development time, exceed the performance of that system and surpass it significantly. So we can approach human-level accuracy on many test sets. Okay, so what do these applications look like? This is a cartoon that tries to capture the essential components of the training algorithm. There was a question about stochastic gradient descent before. The idea is that you have a training data set. You have some input and output pairs that you're trying to learn from. You're randomly selecting them. So the shuffle operation is just a random sample of the training data set. You assemble those together into a mini batch. You get parallelism from that. You run this analytical gradient computation over the model called forward propagation, back propagation. These are sequentially dependent. You run an optimization step where you update all of the parameters in the model. So you make a small change to all of the weights in the model. And then you repeat this over and over and over again. So just maybe to go back to the question around how is this different from gradient descent. In gradient descent, you would usually especially in batch gradient descent, you compute the gradient over the entire training data set rather than just a sample. So you'd probably end up with a very similar result, but you just end up doing a lot more work for every step. Okay. So just wanted to make sure that everyone's on the same page in terms of what these applications look like. I talked about the performance requirements a little bit before. We're seeing that bleed into this figure here around the concept of data parallelism and model parallelism. So if you want to run these really efficiently, really in a high performance way on a large computer, we need parallelism. Modern computers need a lot of parallelism, so where do we get that from? In this algorithm, it comes from the idea that we're processing multiple samples simultaneously, the mini batch, and also that there's inherent parallelism in the model, or model parallelism. I'll talk a little bit more about that. Okay, so let's look at some statistics. So this is the training dataset size that we used for the DeepSpeech system. It used about 12,000 hours of audio. That was augmented up to about 250,000 hours of audio. It's actually kind of embarrassing to look at these numbers, that these systems need such a large amount of data to train on, especially when you compare them against what a human can do. So listening to 27 years of audio straight back to back in order to learn how to recognize speech is actually very inefficient. And there's an important point in here that we've gotten to this point after scaling up the data set, scaling up the model. We needed to scale up the data set very significantly. So these methods work really well in the large data regime. And if you don't have a large training data set, especially a high quality labeled training data set, it's much more difficult to make progress. Okay, so to augment this particular data set, we take recordings of people, maybe from an environment like this. Maybe they're giving a talk. We have a transcript that's been labeled by a person. We then combine that with background noise. So we might play music in the background. We might play other people talking. And that's what I mean by augmentation. Okay. I also wanted to look a little bit at the computational requirements of this training system. So here I'm using work in terms of floating point operations, not floating point operations per second, but floating point operations total required to train one of these models. This is like the total amount of computational work we have to do to go from an uninitialized model to a fully trained model. So you can kind of just see some interesting points on here. One is from this DS1 point here. This is the first version of the system. It took about maybe 4 exaflops, 6 days to train on 4 GPUs. And And it did reasonably well. It did about as well as the previous hand-designed system that we had at Baidu. Increasing it by about an order of magnitude, going from about 4 exaflops to 25 exaflops about, significantly reduced the error rate again. So the DeepSpeech 2 system was something like, I think, about 50% lower error rate, relative lower error rate than the original system, and by increasing the computational requirement by about a factor of 10. So it's actually an interesting experiment, or an interesting thought experiment, to ask how far could we push this? If we really wanted to, how far could we run these models? Is this actually a very big system? It's somewhat of a large system. It was very difficult to map it to even 16 GPUs, but you might want to ask, how far could you totally go? We might think about running not for 5 days or about a week. We might think about running for about a month. We might also just think about what is the biggest type of system that we could build. So we could step up from 16 to 128 GPUs. If you look at how big are the systems that are available in data centers, they're about another order of magnitude on top of this. So they're about 16,000 GPUs. I think the largest machines that I've ever seen in the world are about 100,000, but I think it'd be hard to justify that for a problem like this. That would be extremely expensive. So there's something like 4 orders of magnitude difference here. If we wanted to, there's an opportunity to make these systems much larger, run on much larger data sets, and run much larger models than we're currently doing and we're currently able to do.
What GPUs are these statistics?
These are using the NVIDIA Maxwell GPUs. They're the Titan X Maxwell GPUs. I think they're GM 102, I think, 100 or 102. There are newer generations, of course, that are out. You do get factors of maybe 2, probably up to 10 eventually for single GPU performance. I'll talk about that a little bit later. But it's going to be very hard to get 4 orders of magnitude with just improvements in a single GPU. Okay. So this is really the most important result that we have. And I want to take a few minutes to explain this figure. This is really important. So I mentioned previously, these really large-scale systems. Why do we think that would be useful? I mentioned kind of at a high level previously about this point of bigger models, bigger data sets, getting better accuracy. Where is the result? So this is the result for the speech recognition task that we have. So the y-axis here is an error rate metric. It's the word error rate metric. It's how many words are classified correctly out of a sentence. On average by the model. The x-axis is the training dataset size. This is the unaugmented training dataset size. So it ranges from about 100 hours to about 10,000 hours. We're plotting this on a log-log scale. And we see approximately a linear relationship. Just these curves, they're for different development sets or different data sets. So we think of the red line here as being an easier data set than the blue line. But we see that in both cases, performance gets better following an approximate power law with the data set size. We're also increasing the model size here. So you can kind of think of the x-axis here as being proportional to the amount of compute that you need to do. The total amount of computational work on the previous figure. And so there are 2 hypotheses in here, right? One is that this isn't just speech, this isn't just images, this isn't Go, this is everything. This is many applications. The other hypothesis buried in here is that this relationship will continue out for several more orders of magnitude.
It seems to be a square root law. Is that right?
It seems to be a square root law.
Because you have 2 orders of magnitude on the horizontal axis and 1 on the vertical axis.
I think when we actually do try to fit an exponential to this, we end up getting about a 40% relative reduction per order of magnitude in the data set size. So I think it still is an exponential relationship. It does seem like it gets a little bit weaker out here, but I will say that out here, these are harder to do these experiments, and so there are fewer hyperparameters that are being tested over here because these experiments are much more expensive. I think it's to be seen whether this continues. I think it would be very interesting and very important to do this similar type of experiment in a rigorous way for more applications. I don't think we don't have enough data to conclude this, but this is what we're proposing right now. Go ahead. So the question is the complexity of the model proportional to the GPUs? It roughly scales up with the data set size. You have to do a search over the depth of the model and the size of each layer to basically be able to absorb enough of the data, or a larger data set size. We haven't done enough, I think, careful analysis of that to try and determine what the relationship is. I think the high-level point is that it does grow as the data set grows, but whether it's growing linearly or a square root relationship or something like that, we don't have that level of granularity right now. It does grow with the data. Okay. So I think it's really important for people to understand this. This is what it took to get from 1 GPU to 40 GPUs. There's a potential to go to faster GPUs. There's a potential to go to a much larger scale system as well. And it's a really interesting story here. Like, if this is actually true, it's a really nice story. It means that you don't need to have clever algorithms to make progress on AI applications. It means you just need a faster computer, which is a really interesting result. Okay, so I want to spend a little bit of time talking about what this could potentially enable. So we've talked about applications that have been successful so far. What are we looking at as clear next steps in terms of applications? So this is a figure that I think tries to capture a set of related problems that I think we've come to the conclusion at Baidu that are related to recognition problems. So if we're able to do recognition well, especially in the context of speech-powered interfaces. So the idea here is, you'd like to be able to talk to your computer. It's not good enough that your computer just understands you, just transcribes what you tell it. It's actually able to hold a conversation with you. So what are the problems buried inside of that? The two big ones here are dialogue and generation. And both of them are pretty interesting. Excuse me. Both of them are pretty interesting. Dialogue, excuse me, sorry. So dialogue is actually probably the more difficult one. If you had to classify these, I think you would say that recognition is probably the easiest. It's a many-to-one mapping. Generation is hard, but not the hardest. It's a one-to-many mapping. And dialogue is a many-to-many mapping, and it's much more difficult. So let's dive in a little bit in terms of these two problems. So this is the idea behind generative models if people haven't seen this before. So the example here is using, again, image recognition. You can use different types of data. I just think for slides, it's much easier to look at images than playing sounds. So whereas a discriminative model, you start with an input image and you generate a class, you generate a description. The generative model goes the other way. You start from a description of what you want, and the model will generate an image for you. And really, you think about this as, for the discriminative model, there's a space or a set of all possible images of cats, and you'd like to have a mapping from any point in that space into the class. Here, you're going the other way. And so there is some natural ambiguity here. When you say cat and you give it to a generative model, you ask, which one did I actually mean? And so you think of producing a distribution over all images of cats, which ones are more like cats, less like cats, rather than just having a single possible output. And this ambiguity is what makes this problem more difficult, although there has been a lot of progress on this. So these 2 points here are specific techniques for doing this. The figure on the left is called a generative adversarial network. The figure on the right is produced by a variational autoencoder. These are two specialized techniques for doing this. I think of these as the two leading state-of-the-art approaches for doing this. And they're actually starting to work. I think the example on the left is actually very impressive in the sense that you can give it a sentence and produce images that actually do look like what you're describing in the sentence. The problem with these models is that they're just very difficult to train. They're just very complicated and very difficult to train. Variational autoencoders are conversely easier to train but produce a little bit worse results. This is an area that I feel like it's right on the edge of starting to work. There are a lot of detailed technical problems buried in both of these related to the diversity of the data that's being produced and issues with producing continuous samples, so not just blurring together all things that look like a flower together, but actually producing a unique, distinct image of a flower. There are hard problems like that buried here, but there's been quite a lot of progress here. So for dialogue, this is even harder. You think about having text as an input, text as an output, and interacting with context, so interacting with some information about the conversation, and also potentially interacting with a system that you're designing. So interacting with the computer, pushing all of the buttons on the computer so that it accomplishes what you want it to. This is an even harder problem. But the thought is that if we can make progress on generative models, we've made progress on recognition problems, this is something that's would be a potential next step after that. Okay. And very difficult problems that are buried in here are related to the diversity of the outputs. Like, if you train these models, you see a very common result that they just end up producing generic responses, like "I'm sorry" as an answer to every single question, or "I don't know the answer" as the answer to every single question, because that's a very high probability and a very common thing to do. And just the difficulty in getting data sets for realistic applications is another really big problem with this. People use things like movie scripts to model dialogue between people, but they're not realistic. They're not matched in terms of the domain with a conversation that you'd really have with another person, or especially with a device that you're trying to accomplish a task with. So these are two big important problems that are buried here. So we looked a little bit at these applications, what we're able to do, what we could be potentially able to do if we can make even more progress on deep learning, scale things up even more, get even better accuracy for these applications. So we need some tools in order to accomplish this. So the last part of the talk is going to focus on some of the tools, just kind of surveying at a high level some different components that are very obvious improvements that we could make. So we need a battering ram to break through the wall. So we can look across the entire hardware-software stack. This is what the stack looks like for many AI applications. We go from applications built on machine learning, built on optimization, programming models, compilers, distributed systems, processor microarchitecture, circuits, and semiconductor devices. We look across the entire spectrum here to see where there are opportunities to make progress. So let me just go over a couple of them. One is around semiconductor devices. Right now, if you look at these applications, what is the performance limit? It's actually sometimes difficult to figure out, but it actually comes out to be a simple answer for these applications. It's all limited on the energy that you need to access memory at different levels of the memory hierarchy. So you can see this like very simplistic model here of the energy required to access DRAM as being about 2 orders of magnitude higher than the energy required to access a register, and then for a global cache, it's something in the middle. And really what you want to do for these applications is you want to store the entire model in the lowest possible level of the memory hierarchy. So you want all of the weights to be here all of the time. And if you do that, then there's about a factor of 100 difference in performance that you can get. All of these processors right now end up being power limited. So you end up, and there's another effect going on here, which is that you might ask, like, is it power in memory access or data movement, or is it power in the math, power in the logic? The logic power is about an order of magnitude lower than this. even for somewhat large operations like floating point multiplications. So really, the opportunity in hardware is getting as much of the model into the lowest levels of the memory hierarchy, or making the lowest levels of the memory hierarchy bigger. So there's a clear opportunity in doing this. People are starting to do this where they're trying to integrate DRAM technology with logic. So trying to reduce the wire links from logic to DRAM. High bandwidth memory is a particular technology that does this. The step beyond this, if you could actually do it, this is currently not economically feasible. This is not realizable in real, like a real fab. If you could glue the processor logic directly onto the DRAM and just get wires directly going from floating point units directly into DRAM cells or directly into some other type of memory cell, this would be a really huge benefit, but it's currently science fiction. And doing something other than this, there probably won't be very radical improvements. There will be incremental improvements, but not radical improvements. Okay, so that was processor architecture. Or semiconductor devices. There's a couple other trends in here that are important. So one is around the move from somewhat wide parallelism to even wider, even more structured parallelism. So moving from SIMD to kind of array-based logic, where you just get rid of all of the memory accesses and increase reuse. So having specialized data paths for that. Really, another way of reducing the memory or the amount of energy that's spent on memory accesses is just compressing the model. Just using a lower precision representation, using a sparse representation of the model, and then using that to store it in the lowest levels of the memory hierarchy. And you get big advantages if you're able to do this. It's actually kind of interesting. You're not getting, for low precision, you're not getting really an advantage because the multiplies are cheaper. It's because you're moving less data. Okay, so I'm looking at, so the next one I'm going to look at is for distributed computing. We see this really interesting trend where people started running these applications in high-level frameworks on CPUs. The introduction of some relatively simple low-level libraries like cuDNN or cuBLAS for NVIDIA GPUs and equivalents for other processors made it possible to get model parallelism to be used on single GPUs. There's abundant model parallelism here, but there are no equivalent software interfaces that let you map this model parallelism onto groups of processors. So this layer of the software stack is just missing, and we're losing out on a lot of parallelism that we have because of this. So I'm going to go over maybe two more of these, and then I'm going to conclude for questions. Let's see. So there's another one in compilers I think that's worth mentioning here. One really interesting aspect of these applications is that you get the entire compute graph. This isn't like a dynamic programming language where there's an interpreter and the user is doing anything and you can't make any assumptions. Here you get the entire compute graph specified up front, and you ask the system to evaluate it. And other than a few exceptions, it never changes. So unlike before, unlike many other applications, you have this very clear definition of the program that you're trying to execute. But we don't have software systems, we don't have compiler systems yet that can automatically map these very complex dependency graphs that represent the model onto some very complicated parallel hardware like a GPU or other parallel processor. So there's a clear opportunity if someone is able to build this software stack that does this mapping automatically. It doesn't even have to be a very good job. Currently, we're not even able to do it because people have to do this by hand, and it's very slow to do it by hand. So in practice, we just don't do it most of the time. Okay, let's see, I'm going to skip that one. There's one more in optimization that I wanted to mention here. So this is a really confusing point, but I just wanted to bring it up here because people get confused on this point so much, and there's actually an opportunity here that isn't really obvious. If we looked at the previous figure about this application, where does data parallelism come from? It comes from the idea that we have a mini batch, the idea that we're working on multiple samples simultaneously. So we see this actually very strange relationship with the mini batch. You might ask, and a lot of people do ask, why can't we just make that arbitrarily large? Why can't we just, increase the amount of parallelism that we have in our application by just forming a larger mini-batch? And the reason that we can't is because stochastic gradient descent is really a sequential algorithm. It needs the current update in order to make a good decision for the next update. And so empirically, what you see is if you increase the batch size, the total time to train the model, or the total amount of work that you do to reach the same level of accuracy, it's flat for a while, and then it increases linearly and then superlinearly. And so you end up basically doing more work to get more parallelism, and it's not actually effective. And so there's been a lot of work on optimization for these problems. There's been a lot of work on developing specialized variants of stochastic gradient descent that try and do better from an accuracy perspective. As far as I know, no one has ever asked the question, can we create a stochastic gradient descent variant that just increases the amount of parallelism? We don't care about accuracy. Can we form the problem such that, can we change the optimization algorithm in a way that makes it more parallel? I don't know that anybody's really answered that question or asked that question. So there might be an opportunity there. Okay, so I have a lot of these different points, but rather than go through all of them, I think I'll probably end here and take questions.
Isn't the wall now the size of the data set? Don't you have to be a Baidu-sized company with that amount of data to train a model successfully?
It's a good question. So the question is, do we have to be a large internet company to train these data sets? We did an interesting experiment, or an interesting analysis, which is how much did we spend, how much money did we spend on various components of the system? So the interesting point was that we actually spent more on the computer than we did on the data set. And that's not to say that the computer was cheap, but the idea that, I think a lot of people have a misconception that unless you're a giant internet company, you can't afford to do this work. I think I'd modify that and say, if you can afford a large supercomputer, you can afford to do this work.
Hi, thanks for the nice talk. I have a question. You mentioned that the memory bandwidth is the limiting factor in getting more performance in deep neural networks. Is this general for most of the neural network designs, or, I mean, because my only experience is with convolutional neural networks, which is heavily compute bound, and getting more computations mean better performance?
Right, so the question is the idea of things being memory bound true for all networks, or only some types of networks? It definitely varies from network to network. I think of this in terms of the amount of computational reuse in the network, where convolutions have a large amount of reuse, and other things like fully connected networks or recurrent networks have less reuse. But still, even for convolution networks, you still have this effect where if you want to absorb a larger data set, you still need a bigger model. And so, if you, let's see, I think you will usually reach a point where you can become limited by the memory system for many of these models, even with convolutional networks.
Maybe one more question? Speak up.
So we've seen kind of a movement towards companies like Google with TensorFlow open sourcing some of the deep learning. How is that kind of impacting, what's going on at Baidu and the way other companies do that?
Sure. So maybe what is the impact of open source frameworks for deep learning impacting the industry? I think it's still in a development phase. I think there still isn't a consensus about what the right programming abstractions are. And also, not all frameworks have the best optimizations in them yet. So I think there's so many, you might have seen there's just so many of these different frameworks. Like Baidu has, as far as I know, 4 frameworks internally. We've released 1 externally. And if you look across the community, there are like 50 or 100 different frameworks. I personally think it's a much better situation than we were in 2 years ago. when we didn't have a lot of these frameworks. I think it's still in a rapid development phase, and you won't see standardization for at least another several years.
Great. Please join me in thanking our speaker.